You know that feeling when you're wrestling with something new? Maybe trying to wrap your head around a complicated spreadsheet or a really dense article, and your brain just feels like it's hitting a wall.
Yeah, like it's completely full.
Exactly. It's like trying to cram too much information into too small a space. Well, there's a fascinating reason why that happens, and it's all tied to how our brains handle learning.
And what's interesting from a, well, scientific perspective is that this feeling of being overwhelmed isn't just, a subjective thing. It points to a real limit in our brain's ability to process information actively.
A hard limit.
Pretty much.
Yeah.
When we push beyond that limit, learning becomes significantly less effective. You just can't take it all in.
Exactly. And you, our ever-curious listener, actually steered us towards some pivotal research in this area. We're diving into the work of Fred G.W.C. Paz and Jeroen J.G. Van Marienboer, specifically their groundbreaking 1994 paper, Instructional Control of Cognitive Load in the Training of Complex Cognitive Tasks.
A class.
It really digs into why tackling complex subjects can feel so mentally draining. And more importantly, it offers insights into how we can navigate those challenges.
If we step back and look at the bigger picture, this research is fundamental to understanding how we can design better ways to teach and learn. It highlights that effective instruction needs to consider the learner's mental processing capacity. It's not optional.
So our mission today is to really get to grips with this concept of cognitive load. We want to understand what it is, what makes it skyrocket when we're faced with complex tasks, what the downsides are, and then crucially, explore some practical strategies for managing this mental effort.
Helping people learn better, basically.
Ultimately, yeah, we're hoping to equip you with some knowledge that can help you learn more efficiently and, fingers crossed, feel a bit less like your brain is going to melt when you're tackling something new. Okay, so let's start with the basics. What exactly is this cognitive load that the paper talks about?
Okay. The core definition is the total amount of mental effort being used in the working memory at any one time.
Working memory, like short-term memory.
Essentially, yes, the mental workspace where you hold and manipulate information. But as you might imagine, cognitive load isn't a simple single number. The authors describe it as a multidimensional idea.
Multidimensional. Okay, that sounds like there are a few angles to consider. Can we break down what those different angles are?
Absolutely. The paper talks about factors that cause cognitive load and ways we can assess or measure it.
Right. Cause and effect, kinda.
Exactly. When we look at measurement, they identify three key aspects: mental load, mental effort, and performance. Mental load refers to the demands that the task itself puts on your working memory.
So the inherent difficulty.
Precisely. Think of it as the complexity of what you're trying to learn or do.
Right, like trying to solve a really intricate puzzle. The puzzle itself has a certain level of inherent difficulty, loads of pieces, tricky connections. That's the mental load.
Perfect analogy. Now, mental effort is the amount of your mental resources you actually dedicate to working on that puzzle.
How hard I'm trying.
Exactly. You could just stare at the pieces, low effort, or you could really concentrate, try different combinations, high effort. The focus and energy you invest are the mental effort.
Okay, so the puzzle, the mental load, might be incredibly complex, but I might be distracted and not really trying very hard, low mental effort.
Yeah.
Or the puzzle might be relatively straightforward, low load, but I could be putting in a huge amount of effort to finish it as fast as possible, high effort.
Exactly right. And then performance is the result. Did you complete the puzzle? How many errors? How long did it take you?
The outcome.
Right. Performance reflects both the puzzle's difficulty, the mental load, and how much effort you applied. And it's important to realize someone might maintain good performance on a difficult task, high load, by simply exerting a lot more mental effort.
Ah, they compensate.
Exactly. But this compensation can be really taxing and unsustainable long term.
That makes total sense. So what makes these puzzles, these complex tasks, so mentally demanding in the first place? What are the key drivers of high cognitive load according to the paper?
Well, the paper highlights several characteristics of complex tasks. One major factor is the number and the nature of the individual skills or sub-skills that are involved.
Okay, sub-skills, like
Yeah.
little component parts.
Yes. Think about learning to bake a complicated cake. You need to understand the recipe, measure ingredients accurately, mix them correctly, control the oven temperature, maybe decorate it.
Lots of steps.
A lot of steps. A task with many of these interconnected steps is going to require more mental processing, more cognitive load than a simple one, like just making toast.
Definitely. Trying to keep track of all those different elements when you're just starting out must feel overwhelming. Measuring, mixing, timing.
Yeah. And it's not just about the sheer number of skills. The consistency of these skills also plays a crucial role.
Consistency. How so?
The authors distinguish between recurrent skills, which you perform in a relatively consistent way across different situations.
Like using the measuring cups the same way each time.
Pretty much. And non-recurrent skills, which need to be adapted depending on the specific problem you're facing. Tasks with more non-recurrent components tend to be much more demanding mentally.
Okay, I need a clearer picture of that difference. Can you give an example?
Certainly. Let's take computer programming again. Knowing how to write a basic for loop or how to declare a variable, those are pretty recurrent skills. You'll do them in a similar way in most programs.
Okay, standard building blocks.
Right. However, figuring out how to break down a complex problem into a series of logical steps or designing the overall structure of your software, those are non-recurrent skills. They vary greatly depending on the specific programming challenge.
Ah, the strategy part.
Exactly. Similarly, in statistics, knowing how to perform a specific calculation, like a t-test, that's recurrent. But deciding when a test is the appropriate statistical tool to use for the specific data and research question, that's a non-recurrent strategic decision, much harder.
Okay, I see. So tasks that have a lot of elements that change and require flexible thinking, adapting on the fly, those are the real brain drainers. What else contributes to this high mental load?
Another significant factor is the complexity of the goal hierarchies involved in the task.
Goal hierarchies. Sounds complex already.
It just means that many complex problems aren't solved in one go. They require achieving a sequence of sub-goals to reach the final solution.
Okay, steps within steps.
Exactly. Think back to programming, calculating an average. First, you need to figure out how to access the numbers, that's sub-goal 1. Then you need to add them all up, sub-goal 2. Then count how many there are, sub-goal 3. And finally, perform the division, sub-goal 4.
Right, you can't do step 4 before step 2.
Precisely. Each of these is a sub-goal that needs to be accomplished in order. The more layers and the more interconnected these sub-goals are, the greater the mental load on the learner. It's like a project with multiple dependencies.
Or like a recipe with multiple stages, where each stage has its own set of mini steps you need to follow. First make the filling, then make the crust.
Exactly that. And the paper points out that when novices are faced with these complex goal structures, they often rely on what are termed weak methods.
Weak methods? That doesn't sound good.
Well, they're general strategies that work sometimes but aren't very efficient. A common one is means-ends analysis.
Means ends. What's that?
This is where you constantly compare your current state to your desired goal state and try to perform actions that reduce the difference between them.
Okay, like, I want to be there. What's the next step to get closer? Sounds logical.
It seems intuitive, yes, but it can actually create a significant amount of what's called extraneous cognitive load.
Extraneous load, as in unnecessary load.
Exactly. Extraneous cognitive load is mental effort that doesn't directly contribute to learning the core skills or knowledge. It's wasted effort, in a way.
So how does means ends analysis cause that?
Well, with means-ends analysis, a lot of mental energy is spent simply identifying these differences between current and goal states and trying out various actions to close those gaps. You're focusing heavily on the goal and how far away you are.
Right.
And that focus away from understanding the fundamental characteristics of the problem itself. Things like recognizing patterns from past problems or remembering what moves worked in similar situations before.
So instead of learning the underlying principles of how the puzzle works, I'm just fixated on finding the next piece that fits right now.
Precisely. This high extraneous load can actually prevent novices from paying attention to the very information that would help them build a deeper understanding of the relationships between different elements of the problem and the effective strategies for solving it.
That's almost paradoxical. You'd think that actively trying to solve the problem would be the most direct route to learning.
And that's a key insight from cognitive load theory. Traditional teaching often emphasizes giving learners a lot of these full, goal-oriented problems to solve right from the start.
Yeah, practice makes perfect, right?
Well, maybe not always. For novices, this approach can inadvertently overload their cognitive system with this extraneous load, hindering their ability to learn effectively. The paper references quite a bit of research supporting this: Sweller, Van Marion, Bohr, Paz, others, across various fields like programming, math, physics.
So if our mental processing power is getting tied up with all this extra, unproductive work, what are the real downsides for learning? It's not just about feeling mentally tired, is it?
No, definitely not. The fundamental problem is that excessive cognitive load leaves less available mental capacity for the essential processes of learning,
Like what?
like understanding the core concepts, developing efficient problem-solving strategies, and connecting new information with what you already know,
Okay.
building those mental models.
It's like trying to run multiple demanding applications on a computer with limited RAM. Everything slows down, and some processes might even crash.
That's a perfect analogy. The actual aha moments, the deep understanding that we're aiming for, just don't have the mental space to occur when your working memory is overloaded.
The resources are being consumed elsewhere.
Exactly. They're being consumed by managing the immediate complexity and the often inefficient search for solutions rather than being used to build robust, transferable knowledge and skills.
This all makes a lot of sense in theory. But how do we actually know when someone is experiencing this high cognitive load? How do we, measure this mental strain?
That's a really important practical question, and the authors acknowledge that it's not always easy to get a clear measure.
Why not?
Well, because of that multidimensional nature we talked about and the complex relationship between performance, load, and effort. Remember the compensation idea.
Right. Someone might perform well but be mentally exhausted doing it.
Exactly. They might maintain a decent level of performance on a difficult task by simply working much harder mentally, effectively masking a high underlying cognitive load. This is why it's crucial to try and measure mental effort directly, not just rely on observing performance.
So if someone looks like they're getting all the answers right, but seems completely stressed out while doing it, they might still be experiencing high cognitive load.
That's a good way to put it, yeah. Their behavior might suggest high effort. The paper outlines two main categories of methods for trying to gauge this effort. The first involves subjective measures,
Subjective, like asking them.
pretty much using rating scales. The idea here is that individuals can actually reflect on their internal state and report how much mental effort they felt they were expending.
Can people really do that accurately?
Surprisingly well, according to some research cited, like work by Gopher and Braun. They found people can provide fairly reliable numerical ratings of their perceived mental load and effort.
So simply asking someone, on a scale of 1 to 10, how hard did you have to think about that, can actually give you meaningful information.
Yes, within certain limitations, self-report can be a valuable and, importantly, practical tool, easy to implement.
Okay, what's the other category?
The second category encompasses psychophysiological measures.
Psychophysio.
Oh.
Okay, body stuff.
Yeah, exactly. These techniques look at the relationship between mental effort and physiological changes in the body.
Like heart rate.
Heart rate variability, specifically. Studies by Asman, Mulder, and Mulder, for example, found that as mental effort increases, there's a tendency for the variability in the time between heartbeats, particularly in the mid-frequency range, to decrease.
Interesting. So less variability means more effort.
Generally, yes, that's the finding. Other physiological indicators, like changes in pupil diameter pupils, tend to dilate under higher load, and specific brainwave patterns measured by EEG can also provide insights into cognitive processing.
Wow.
Essentially, when your brain is working harder, it can affect these subtle bodily responses.
That's fascinating. So you could potentially use these physiological responses to get a more objective reading on how hard someone's brain is working, beyond just what they say they feel.
Precisely. Combining these different approaches, subjective ratings, performance data, and physiological measures, ideally gives us a more complete picture of a learner's cognitive state.
Okay, so we have a better understanding of what cognitive load is, what factors in complex tasks drive it up, and some ways we can try to measure it. Now, for the really critical question, what practical steps can we take? How can we design instruction or learning experiences to effectively manage cognitive load and help people learn more successfully?
This is where the paper gets really practical. The authors emphasize two primary instructional goals that stem directly from our understanding of working memory limitations and the importance of applying knowledge in new situations transfer.
Right, okay. What are the two goals?
The first, as we've discussed quite a bit, is to optimize or really reduce cognitive load, especially for learners who are new to a complex task. Get rid of the extraneous load.
Makes sense. What's the second?
The second, which is equally vital, is to guide the learner's attention in ways that promote the ability to apply their knowledge and skills in novel contexts, what's known as transfer. Near transfer to similar problems, and far transfer to quite different situations.
Transfer is really the ultimate goal, isn't it? It's not just about being able to solve the specific problems you were taught in class, but about having a deeper understanding that allows you to tackle new and different challenges out in the world.
Absolutely. That's the mark of real learning. So let's look first at how we can reduce cognitive load. One key concept they discuss is the distinction between automatic and controlled processing.
Automatic versus controlled. Okay.
This comes from the work of Schneider and Schifrin. Controlled processing is slow, requires conscious effort and attention. It's what we rely on when we're learning something new. It uses up working memory capacity.
Like learning to drive a manual car. Clutch, gas, shifter. Lots to think about.
Exactly. Automatic processing, in contrast, is fast, happens without conscious thought, and requires minimal effort or working memory resources. It's what happens when we've practiced a skill so much it becomes second nature.
Like tying your shoes. When you first learned, it took intense concentration. But now you can probably do it while talking.
Perfect example. So, in learning complex tasks, a key aim is often to automate some of the more routine or foundational aspects, the recurrent skills we talked about,
Why?
to free up our limited mental resources, our working memory capacity for the newer, more demanding, non-recurrent parts of the task.
Make room for the hard stuff.
Precisely. This shift from controlled to automatic processing is what they call rule automation, and it primarily occurs through consistent practice. Lots of it.
So the more I practice those consistent recurrent skills we talked about earlier, like maybe basic syntax in programming or multiplication tables in math, the more automatic they become and the less mental energy they consume.
Exactly right. And this frees up capacity. The four-component instructional design model, the 4C model, which Van Marienboer was heavily involved in developing, provides a structured approach to achieve this.
The 4C model. Okay.
It involves a detailed analysis of the complex task first to identify both the recurrent and non-recurrent component skills, plus the underlying knowledge needed. Then, the design phase focuses on developing instructional strategies that specifically facilitate the automation of those recurrent skills.
Through practice.
Through focused practice, yes, to reduce overall cognitive load while simultaneously addressing the non-recurrent skills in ways that promote deeper understanding and transfer.
Okay, so the idea is to make the routine parts effortless so our brains have more processing power available for the more complex and novel aspects of the task. That makes a lot of sense. Now, what about that second crucial goal? How do we redirect attention in ways that help with transfer? How do we build that deeper understanding?
This is where the concept of schema acquisition becomes central.
Schemas, what are those exactly?
Schemata or schemas are like mental frameworks or organized networks of knowledge that we develop through experience in a particular domain. They allow us to recognize patterns in problems and apply appropriate solutions much more efficiently.
So like mental shortcuts or templates.
Kind of. Think of it as building up a well-organized mental library of problem types and the strategies that are most effective for solving them. Experts have highly developed, sophisticated schemas in their field.
So instead of having to figure things out from scratch every single time, if I have a good schema, I can recognize a familiar type of problem, like, oh, this is an average calculation problem, and I already have a good idea of the steps involved.
Exactly. As we become more expert in a domain, our problem solving tends to shift from being search-driven, where we're kind of fumbling around, trying out different possibilities using those weak methods.
Like means-ends analysis.
Right. It's just to being schema-driven, where we recognize the type of problem and can quickly access a general approach, a stored solution pattern based on past experience.
Much more efficient.
Much more. The authors emphasize that learners actively construct and refine these schemata through their experiences, especially when they encounter both successful and unsuccessful attempts at solving problems. You learn what works and what doesn't.
So failure is part of building schemas too.
Absolutely. Analyzing why something didn't work helps refine the schema. And importantly, the automation of those recurrent skills we discussed earlier indirectly supports the development of these more complex schemata for the non-recurrent skills by freeing up those precious cognitive resources. If you're not struggling with the basic mechanics, you have more mental bandwidth to notice the deeper patterns, to reflect on the strategies, and to build those robust mental frameworks.
So by making the basic operations automatic, I can focus more cognitive energy on understanding the underlying structure and the overall strategy for tackling more complex, non-recurrent problems.
Precisely. Now, the paper goes on to discuss several specific training strategies that have been shown to be effective in implementing these principles, reducing cognitive load, and redirecting attention to promote schema acquisition.
Okay, this is where it gets really interesting. The practical stuff. Let's hear about some of these strategies.
One notable approach is the hierarchical approach, championed by Fredrickson and White. The core idea here is part-task training. You break down the complex task into its essential component skills.
Recurrent and non-recurrent ones.
Yes, and then provide practice on these individual skills and related strategies in a specific logical order, gradually building up complexity until the learner is performing the complete task.
So learn the parts before the whole.
Exactly. They use the example of a complex video game called Space Fortress. Learners initially practiced the specific subskills, like just detecting and destroying the mines, before they were asked to play the full, multifaceted game, which involved flying, shooting, dealing with mines, etc.
And did it work?
Yes, this type of part-task training was found to lead to better transfer of skills, better performance on the whole task later, compared to learners who only practiced the whole game right from the outset.
That makes intuitive sense. You need to master the building blocks, the chords on a guitar before you can construct something more elaborate, like playing a whole song.
Exactly. Now, contrasting that slightly is the emphasis manipulation approach, developed by Gopher, Weil, and Siegel. This involves training learners on the entire complex task from the start.
Oh, whole task training then.
Yes, but with a twist. They intentionally vary the amount of emphasis placed on different subcomponents of the task during different phases of training.
How does that work?
Using the Space Fortress game again, they might have learners initially focus primarily on mastering the ship's control dynamics in one phase, really concentrating on smooth flying, even if they ignore the mines for a bit. Then, in a later phase, they shift the emphasis, telling them to really focus on effectively handling the mine threats, maybe even sacrificing some flying elegance.
So you're still doing the whole thing, but your attention is guided.
Precisely. You're manipulating their focus within the whole task. And interestingly, they found this seemed to particularly benefit learners with lower initial abilities. These learners, using emphasis manipulation, managed to achieve performance levels closer to those of higher ability individuals who trained without this specific emphasis shifting.
It's almost like focusing on different sections of an orchestra during rehearsal to make sure the strings are strong, than the brass before the final performance. Interesting. What else?
Another fascinating set of strategies involves the use of goal-free problems, which were extensively researched by Sweller and his colleagues.
Goal-free. How can a problem be goal-free?
Well, instead of giving learners a problem with a specific goal to achieve, like calculate the velocity, the problem asks them to simply calculate the values of as many variables as they can, given the initial information. Find whatever you can find.
Huh. That sounds weird. Did it work?
Yeah. Surprisingly, yes. Studies in areas like physics, specifically kinematics, geometry, and trigonometry, have demonstrated that learning and the ability to transfer knowledge to new problems are often better when using these goal-free problems compared to traditional goal-specific problems.
That sounds completely counterintuitive. How can not having a specific goal actually lead to better learning? What's the theory?
The theory is that it redirects the learner's attention away from that potentially overloading means-ends analysis we talked about, that constant focus on how do I get to that specific answer?
Right, reducing the difference between current and goal state.
Exactly. Instead, the goal-free format encourages learners to work forward from the given information, exploring the relationships between different concepts, applying rules they know, and seeing where it leads. It promotes exploration and discovery.
So they're focusing more on the process and the connections.
Yes, and building those valuable schemata. Because they're not constantly focused on reaching one specific endpoint, the cognitive load associated with that intense goal-directed search process is reduced. This allows them to focus cognitive resources on understanding the fundamental principles and relationships within the problem domain.
So instead of tunnel vision on getting to a particular answer, the learner is encouraged to explore the entire landscape of the problem and the connections within it.
That's a great way to put it. Then there are worked out problems or worked examples.
Yes, I've heard of these, like seeing the solution step by step.
Exactly. Learners are provided with fully completed, well-structured solutions to example problems. Extensive research, again by Sweller and Cooper, Zhu and Simon, has shown these to be remarkably effective, particularly in subjects like algebra and mathematics, and especially for novice learners.
Why are they so good for novices?
Because studying these step-by-step solutions helps prevent learners from engaging in inefficient trial and error or those weak methods. It directs their attention very clearly to the key steps and underlying principles involved in solving that specific type of problem.
So it reduces the guesswork and the load associated with that.
Precisely. It reduces extraneous cognitive load and helps them start building correct problem-solving schemata right away. It might seem counterintuitive, again, isn't struggling better, but for novices, that struggle often leads down unproductive paths and can even reinforce misconceptions.
So the worked example provides a kind of cognitive scaffold.
Exactly. It shows the efficient and correct way to navigate the problem space, allowing the learner to internalize those expert moves. In fact, some studies mentioned in the broader literature, like one by Zhu and Simon, suggested that using worked examples heavily could potentially significantly accelerate learning, maybe even cutting down the time needed for certain math curricula.
Wow. So sometimes seeing how an expert does it first is much more beneficial than just banging your head against the wall trying to figure it out yourself.
Especially in the initial stages of learning a complex procedure or problem type, yes. It provides a clear roadmap and helps build an understanding of the correct approach without overloading the learner with the demands of generating the solution entirely from scratch.
Okay. Are there variations on this?
Yes, building on this idea is the completion strategy introduced by Van Marion Bohr. This involves giving learners partially completed solutions and asking them to fill in the missing steps.
Ah, like Mad Libs for math problems.
Ah, sort of. It's like a middle ground between traditional problems where the learner does everything and fully worked out examples where everything is provided.
So you give them a starting point or a structure.
Right. Studies in areas like computer programming and statistics found this approach can lead to better learning outcomes, including, interestingly, a more effective use of programming templates, those schemata we've been discussing, compared to just generating new programs from scratch.
So they learn the patterns better.
It seems so. The level of completion can be carefully adjusted too. You can start with mostly complete examples and gradually reduce the amount provided as the learner gains proficiency, carefully managing the cognitive load.
So the learner gets some scaffolding, but they still need to actively engage in the problem-solving process for the parts that are left blank.
Exactly. They're actively involved but supported. Finally, there's the strategy of training students in expert-like problem analyses as investigated by Dufresne and colleagues.
Analyzing like an expert, how do you teach that?
This involves explicitly teaching students how to perform qualitative, hierarchical analyses of problems before they even attempt to calculate a numerical answer, thinking about the underlying principles first.
So not jumping straight into the formulas.
Right. They might be guided to answer a series of questions that mirror how an expert would approach the problem. What physical principles apply here? What are the key objects and interactions? What coordinate system makes sense? Often using structured tools like something called the hierarchical analysis tool, HAT, they used for classical mechanics problems.
And this helps.
Apparently, yes. This approach was shown to improve students' ability to make expert-like judgments about problems, categorizing them based on deep structure, not surface features, and ultimately to solve them more effectively.
How does that link back to cognitive load?
The suggestion is that it redirects their attention away from just plugging numbers into equations, which can be a form of means-ends analysis, and towards a deeper, more fundamental understanding of the underlying principles. This focus on higher-order knowledge structure reduces the cognitive load associated with inefficient, formula-driven problem-solving attempts.
So instead of jumping straight into the calculations, you're teaching people to think like an expert from the very beginning, focusing on understanding the nature of the problem first.
That's the core idea. The paper concludes by highlighting that these diverse instructional strategies, hierarchical, emphasis manipulation, goal-free, worked examples, completion, expert analysis, while differing in their specific implementation.
They all share a common goal.
Right. They all work to enhance learning and transfer by either actively guiding the learner's attention towards building those crucial mental schemata, or by strategically reducing the amount of cognitive load experienced during the learning process, or often both.
Makes sense.
They also briefly touch upon a distinction between process approaches, like the expert analysis, which aim to get novices to emulate the thinking processes of experts, and product approaches, like worked examples, which focus more on understanding the final outcome or solution structure. And they note some strategies are more global, affecting overall course design, while others are more specific techniques.
Okay, so what does this all boil down to for you, our listener? What's the key message you should take away from this deep dive into the fascinating world of cognitive load theory?
I think the fundamental takeaway is that understanding and actively taking into account cognitive load is absolutely essential for effective learning, especially when you're tackling complex skills or knowledge. It's not just fluff, it's based on how our brains actually work.
It's a real constraint we need to design around.
Absolutely. By employing instructional strategies, whether you're an educator designing a course or an individual learner figuring out how to study, that minimize unnecessary mental strain, that extraneous load, and instead focus your attention on building a strong framework of understanding, those mental schemata we discussed.
Then what happens?
Then the learning process can become significantly more efficient, probably more enjoyable too, and ultimately less overwhelming for you. You learn better and faster.
So here's a final thought for you to really ponder. How might you apply these principles of managing cognitive load to your own current learning challenges? Think about a specific skill you're trying to acquire right now, or a complex topic you're trying to understand.
Could you break it down into smaller, more manageable parts? Practice the basics until they're automatic.
Yeah, or could you seek out worked examples or partially completed solutions to guide you in the beginning? Maybe find explanations that focus on the core principles before diving into complex applications.
Or perhaps, when you're trying to explain something complex to someone else, could you use these insights? How could you structure your explanation to minimize their cognitive overload and help them build a more robust understanding?
Consider which of the strategies we've discussed today, from breaking down tasks hierarchically, part task training, to using goal-free problems or worked examples, or completion problems, or emphasizing expert-like thinking, which might be most relevant and beneficial in your specific context.
It really offers a powerful new lens, a different way to think about the entire process of learning and instruction. It's not just about putting in hours, it's about learning smart.